Hello, this is the section 5.3 lesson. Section 5.3 is about testing claims about a population mean. Now what we're going to do here in section 5.3 is very similar to section 5.2. The biggest difference is that in this section we're going to be testing about claims about a mean, whereas in section 5.2 we tested claims about a population proportion. Same basic steps are the same terminology is the same. Just that here we're going to be working with means rather than proportions. So to illustrate this, let's look at example 533, where a manufacturer of cheese claims that the mean weight of all of its 12-ounce packages of shredded cheddar is greater than 12 ounces. Okay? So the packages say that they're supposed to hold 12 ounces, but they don't always hold exactly 12 ounces. Maybe it's a little bit more, maybe it's a little bit less. But this manufacturer is claiming that the mean weight of all of these packages is bigger than 12 ounces. So in other words, they're claiming that the packages are not underfilled on average. Well, let's note that in order to know with 100% confidence if this claim were true or false, we would have to go out and weigh every single package of shredded cheddar, add up all those weights, divide by the total number of packages, and we would get our population mean. If that population mean were greater than 12 ounces, then our claim would be true with 100% confidence. Otherwise, it would be false. Well, we obviously can't do that. We can't go out and weigh every single package of shredded cheddar. So instead, what the manufacturer does is they collected a random sample of 36 packages and weighed each. So they took a sample of packages and weighed them. That's relatively simple to do. So they calculated a sample mean of x bar equals 12.05 and a sample standard deviation of 0.15. So they added up those 36 weights divided by 36 and they got this sample mean of 12.05. And then they calculated the sample standard deviation just like we did back in chapter 4 and they got 0.15. So we're going to use this data to test their claim about this population mean at a 0.05 significance level. Now let's stop right here and think about something. We might be tempted to say that the fact that this sample mean is greater than 12 proves our claim, right? Because 12.05 is greater than 12 and the claim is that the mean is greater than 12. It seems to be proven. But we need to take a step back and realize about what we're making a claim about and where our data comes from. This claim is about the population of all 12-ounce packages. This mean comes from a sample of 36 packages. So this data here does not come from our entire population, it only comes from our sample. What this sample mean does prove is that in this sample of 36 packages, the mean is greater than 12. But we're not making a claim about just this sample of 36 packages. We're making a claim about this larger population. So our data appears to support the claim, but it does not prove the claim. We're going to use our hypothesis test to determine to some extent just how strongly this sample data support the claim. So when testing a claim about a mean, there are two basic types of tests. There's the z-test and the t-test. And the biggest difference between them is what type of distribution the sample or the test statistic has. In a z-test, the test statistic is a z-score, so it has a normal distribution. In a t-test, the test statistic is a t-score, so it has a student t distribution. Now, how do we know when to use which type of test? Well, we use the z-test when either the population variance is known, which is rarely the case, so we're almost never going to see this, or if we have a large sample size. Now, just how large the sample size needs to be is maybe a bit subjective, but for our purposes, we're always going to use the t-test. And one reason we're always going to use the t-test is because in the end we're going to let our calculator do all the work. And it's just as easy for the calculator to do the z-test as it is for the t-test. And so we're just always going to use the t-test. So let's talk about this t-test. The purpose of a t-test is to test the claim about the mean of a single population. And that's exactly what we're doing here in this example. We're making a claim about the mean of this population of all 12-ounce packages of cheese. The null hypothesis looks like this. It's mu, which is our population mean that we're making a claim about, equals mu naught, where mu naught is some given number. So notice this null hypothesis looks very similar to what we saw in section 5.2, except that instead of p equals p naught, it's mu equals mu naught. Remember, mu always refers to a mean rather than a proportion. So from our data, we need 3 sample statistics. We need n, our sample size, x bar, our sample mean, and then s is our sample standard deviation. Here's the formula for calculating the test statistic. T equals x bar minus mu naught divided by s over the square root of n. Okay. Now here in this lesson, we won't talk about where this formula comes from. In the book, we talk a little bit more about the theory behind it, but we'll just look at how we use this. Okay. Now in a t-test, we have a critical value and a p-value, just like we had back in section 5.2. The critical value is a t-score, or it's a t-value with n minus 1 degrees of freedom. And these critical t-values come from table C3 in the appendix in the textbook. Okay. The p-value is an area underneath a curve, but it's not an area underneath a normal bell curve. It's an area underneath a student density curve with n minus 1 degrees of freedom. Now, like in section 5.2, how we found the critical value and how we calculated the p-value all depended on the form of the alternative hypothesis. And we had 3 basic forms, one where we had a greater than sign, one we had a less than, and one where we had a not equal to. Here our critical regions are found in the same basic ways in section 5.2, depending on the form of the alternative hypothesis, and the p-value is calculated in the same basic way. If we have a greater than sign, then it's a right-tailed test and the area is to the right of the test statistic. If we have a left-tailed test, then the area is to the left. If it's a two-tailed test, then it's twice the area to the left or the right, which either is smaller. So same basic idea. The biggest difference here is that this area is underneath a student t-density curve, not a normal density curve. So 2 requirements for this test. Number 1, the sample is random. That's always a requirement for any of these hypothesis tests. And then number 2, either the population is normally distributed or n is bigger than 30. Now in this case, we're not given any information about the distribution of our population, but it really doesn't matter because n was 36, which is indeed greater than 30, and so our requirements are met. So let's apply our t-test back to this example. Here's our problem. Now when we do the hypothesis test here, we're going to go through the exact same 5 basic steps as what we did in section 5.2. The first step is always to define the parameter. So the parameter that we're making a claim about is mu. We use mu because it's a population mean. And it's the mean of what? Well, it's the mean weight of all 12-ounce packages. Notice we include this word all here to stress the fact that we're making a claim about this large population of all packages. We're not interested in just these 36 packages in our data. We're interested in all 36, in the population of all packages. Okay. Next, we need to state our claim and our null and alternative hypotheses. So the claim in mathematical notation is that mu is greater than 12. So our null hypothesis is going to be the statement that mu equals 12. Remember, the null hypothesis is like a statement of the status quo. It's what we would expect to be true if we didn't have any data to suggest otherwise. So the packages are labeled at 12 ounces, so we'd expect their mean to be 12 ounces. The alternative hypothesis can be that mu is greater than 12, which is the same as our claim. It's also the statement that's supported by the data, because in our data, our sample mean is bigger than 12. That suggests that our population mean is greater than 12. So there's our null and alternative hypotheses. The next step is to calculate the test statistic. Here's our formula for the test statistic. We just plug our numbers in. Here's our sample mean. Here's mu naught. Mu naught is this number 12 right there. There's our sample standard deviation and our sample size, and that all simplifies very nicely down to the number 2. So there's our test statistic. Third step is we find our critical region, or equivalently calculate the p-value. So the critical value is t sub 0.05. It's 0.05 here because we're told to use a 0.05 significance level, and we have 35 degrees of freedom. That's n minus 1. So if we look up that number from table C3, we get our critical value of 1.69. The p-value is the area to the right of our test statistic. This is a right-tailed test, and so that's how we calculate our p-value. Now this p-value cannot be found from tables that we have available in our book. We can estimate that p-value using tables, but we can't find an exact value. So we need to use software. And here in a bit we'll talk about how we can use our calculator to find that p-value. But when we do that, our p-value comes out to be 0.027. Okay. Fourth step is to come to our technical conclusion. So here's our critical region. Again, it's a right-tailed test, so the critical region is our critical value, comma, infinity. And so our test statistic does indeed lie in that critical region. If we look at the p-value, it's a rather small p-value, which is less than alpha, which was 0.05. And so using either the critical region or the p-value, we would come to the technical conclusion of reject the null hypothesis. Last step is to state our final conclusion in non-technical terms. So we reject the null hypothesis in favor of the alternative hypothesis. The alternative hypothesis was the same as the original claim, and so we would conclude that the data do indeed support the claim. So there we go. That's all there is to doing a t-test. Same basic steps as the one proportion z-test that we did in section 5.2. Just that here we're working with means and standard deviations rather than proportions. Now lastly, let's talk about how we can do this on our calculator. This t-test is built into the calculator. So if you go to the stat menu, then the test submenu, and then choose option 2 for the t-test. Notice that option 1 is the z-test, which works very similar to the t-test, but we're always going to use the t-test unless otherwise specified. So if you hit enter, you'll see a window that resembles this. You see here where it's the t-test. Next thing we have to indicate is how we want to input our information. And we have two options, either data or statistics. If we have the raw data, then we can enter that data into a list, and then we can select that list, and the calculator will find our sample size, sample standard deviation, sample mean, and go from there. But that's not what we have here. We don't have raw data, meaning we don't have the weights of all those 36 different packages. All we have are summary statistics, and so we're going to choose that option, stats. Next, we need to enter mu naught, which is the mean used in the null hypothesis, and then x bar, which is our sample mean, and then sx is our sample standard deviation, n is our sample size. And then next we need to choose the form of our alternative hypothesis. And the alternative hypothesis is that mu is greater than 12, and so we're going to choose this last option, greater than mu naught. Then lastly, we have two options, either calculate or draw. If we select calculate and then press enter, we should get a window that looks like this. So the first row tells us that we just did the t-test. Next row tells us the alternative hypothesis as we entered it. It just allows us to double check our work. We see that that was correct. And then here's our test statistic, t is 2. And then this right here is the most important number for our purposes. It's the p-value. P is 0.0266. And so that gives us our p-value. Next, it outputs our sample mean, standard deviation, and sample size. That does that just so we can double check our work. So there we go. That's all there is to calculating the p-value for a t-test on the calculator. Now, just for fun, let's go back to the t-test menu. Enter the exact same information that we entered before, but now instead of calculating or selecting calculate, select draw. And when you do that, it gives us a window that looks like this. We see our test statistic t equals 2, our p-value right there rounded off to 4 decimal places. And we see here what looks like a bell curve, but that's actually not a bell curve. That is a student t density curve with 35 degrees of freedom. And we see here's our test statistic 2, and the area to the right is shaded. That's because this p-value is the area to the right of our test statistic. And so there, that just gives us a nice graphical representation of where that p-value comes from.